Good morning, everybody. Our class has kind of an interesting combination of mechanism skills. So I wanted to see how yesterday's lecture, which ended off on kind of a rushed mechanism, how yesterday's lecture felt for you guys. Did it seem like a good review? Did it introduce confusions? I'll take that as it was a good review. We've looked at all of the alkene addition reactions that I want to cover. And I know we saw a couple that were kind of new to us. Some of you might have seen a few other reactions that we just didn't cover. The Simmons-Smith reaction is a way that you can make a cyclopropane ring off of an alkene. And it's a good reaction. It's just not one that's covered in our textbook, so we don't look at it as much. Today we're going to move into the alkyne reactions, the reactions with alcohols and alkyl halides. So basically, continuation of addition reactions, and then a segue into substitution and elimination reactions. You guys good with that? Okay. Similar to last time, we had kind of this graphic centered in the middle with reactions sprawling out. I'm going to be doing much the same thing again today. I encourage you again, if you don't think that you've got the organizational skills to make it look like this big graph, then maybe just do a list. Just show each of the reactions. You don't have to rewrite the starting material. But one thing that I am going to do for this series of reactions is I'm going to highlight the distinction between internal alkynes and we'll make one of these, we'll make it a little bit asymmetric. And we're going to look at terminal alkynes. So here I've got 3-methyl. Oh, I guess I didn't need to work too hard, did I? No, that's good, it's good. 3-methyl 2-pentyne, and I've got 1-butyne. And so we're going to show some different reactions. Some reactions which are regiospecific, and so we want to see how the regiochemistry of a terminal alkyne differs. And some reactions that are not regiospecific, so it doesn't matter if you look at them at an internal or a terminal alkyne. But there are some interesting things that can come up from an alkyne that is asymmetric like this, an alkyne that has 2 different R groups connected on either side. We'll follow a similar pattern to what we did last class. So first, let's look at the HX addition. And we're going to have to consider when HX is added in 1 equivalence to the alkyne, and we'll have to consider when it's added in 2 equivalences. When it's added at 1 equivalence, we add H and we add X across one of the pi bonds, and it follows Markovnikov's rule. The H adds to the less substituted side, the halogen to the more substituted side. When we add HX in 2 equivalences, we always generate a vicinal dihalide, a geminal dihalide. The reason that we call this a geminal dihalide is because of its 2 halogens being connected to the same carbon. Anybody a Gemini star sign in here? Just me. Okay. Don't hate me if you hate Geminis. I don't know why I get that hate all the time for being Gemini. Gemini star sign is the twin star sign, and these are geminal dihalides because they're twin dihalides. They're on the same carbon. Markovnikov. Then we can look at our X2 addition reactions. And again, with our X2 additions, we can do this in one equivalence, which is always going to add one halogen to each carbon of the alkyne, and stereoselectively adds them anti to one another.
Wouldn't it be just a single bond?
It uses one of the pi bonds and conserves one of the pi bonds because it's adding just one addition across that alkyne. Does that answer your question?
But it has two halide. What is the bond come from?
So the X2 gets broken across the two carbons of the alkyne. One of the alkyne pi bonds is consumed, and then that halogen bond is broken.
Okay.
Yeah? You sure? I'm not sure that I'm answering it right, or that I'm getting what your question is. If we add two equivalences of X2, we just end up adding halogens all the way around, a tetrahalo product. And I am kicking myself because I realized I made a bit of a blunder. I wanted to do another HX addition reaction to keep us on track with what we did in the alkenes. So I'm going to add that other HX reaction up here. The other condition that we'll consider is HX in excess, so two equivalences or more. I'm going to write that as excess, as well as with a peroxide, ROOR. One of the most common examples of peroxides that you would see here is the hydrogen peroxide reagent. Can someone remind me, with our alkene addition reactions yesterday, what difference did adding peroxide with HX make relative to adding HX alone?
Makes it anti.
Good. This makes the addition product anti-Markovnikov. So instead of having a geminal dihalide on the more substituted carbon of the alkyne, I'm going to have a more substituted, or excuse me, I'm going to have a geminal dihalide on the less substituted carbon of the alkyne. The other reason I'm kicking myself is because I wanted to use that terminal alkyne to highlight a different reaction, but now I've kind of squeezed myself out of any space with it. So that's upsetting. I think what I'm going to do is just kind of elongate the space that I give it, because this molecule makes the best example for these next couple of reactions. I want to look at hydration reactions next. How many different hydration reactions did we have with alkenes? If you look back at that chart we made yesterday, how many different reactions produced a hydrate product? Three of them. Two were Markovnikov, one was anti-Markovnikov. One had a carbocation intermediate in that Markovnikov, one did not. So we have a lot of different useful reagents. With our alkynes, we're only going to have two hydration reactions. One of them uses mercury sulfate, HgSO4, sulfuric acid, and water. The interesting thing about hydrating an alkyne is that at first, you consume one of the pi bonds, so you go from a triple bond to an alkene, to a double bond, and you add an equivalence of water across that pi bond. So you add H and OH. This structure is called an enol. Our last chapter this semester, we're going to do a lot of chemistry with the enols. But this structure isn't really stable. It readily tautomerizes, which is, it goes through structural rearrangement catalytically. Now, 9 times out of 10, structural isomers cannot be interconverted chemically. But these are structural isomers that are interconverted. You can see that the pi bond relocates and the hydrogen from the alcohol relocates.
For the last one you said, is it the mercury SO4 on the top? Or,
Mercury, HgSO4, mercury sulfate.
and then what on the bottom?
Sulfuric acid and water.
Do you use both or is either one or?
Yeah, you would use them all.
Oh, okay.
You would just mix these all into a reaction flask.
I thought you could just do the sulfuric acid with water.
Mm-hmm.
Is that a hydration equation for your alkenes?
It's not, so actually the reagents here are not exactly the reagents we used with the alkenes. So with alkenes, we had oxymercuration reduction. It was a 2-step reaction. First, mercury acetate in water. Second, a reducing agent, sodium borohydride.
So they're an acid.
We also had acid catalyzed hydration.
Yeah.
And this reaction is a bit of a hybrid. This is acid oxymercuration.
Oh.
It's not oxymercuration reduction. It's not a 2-step reaction anymore. And it combines the mercury and the acid all at once. Now, based on what we saw about both the oxymercuration reduction reaction and the acid catalyzed hydration reaction, do you think that this reaction will give a Markovnikov product or an anti-Markovnikov product? Because those two reactions in yesterday's class were both Markovnikov. This is Markovnikov as well. So we're going to add 2 hydrogens to the less substituted side, and we're going to form a carbonyl on the more substituted side. What functional group does that give? Ketone. Every time. We can use mercury sulfate to make a ketone.
What about the alcohol you put in? Like as well?
So it forms that enol. It's an alcohol attached to an alkene, which makes it an enol. And enols aren't incredibly stable. They readily react with a catalyst to form this. So this would be the final product that you isolate. If you ran this in a reaction flask, you would form an enol intermediate, but this is what you'd get at the end of the day.
So if you say, what would happen if this reaction, we just put the ketone and that's it?
Yep, that's the product. Absolutely. It does introduce something interesting, which is to say that ketones can be converted into enols. And we're going to come back and look at that in our last chapter this semester. We're going to look at how carbonyls can become enols and what chemistry we can do with that form. Now, the second reaction that we can do here, the second hydration reaction, is another 2-step reaction. This is the hydroboration oxidation. So we're going to use BH3 and H2O2. Just like last time, this was an anti-Markovnikov addition reaction. So instead of forming a carbonyl on the more substituted side of the alkyne, I'll add a carbonyl on the less substituted side of the alkyne. What functional group does that give me?
Aldehyde.
That's our aldehyde. So once again, we have structural differences produced by these reagents, which in turn makes the reagents useful because now I'm not just limited to doing one thing with them. I've got a lot of different things I can do. All right. Couple of other reactions that we should look at here. One thing that I would like to show you is actually what happens when this internal alkyne reacts with two equivalences of HX. So we know that the HX addition is Markovnikov. But on an internal alkyne, which carbon is more substituted? Neither. They're equally substituted. This adds Markovnikov. Well, which carbon has more hydrogen? Neither of them have any hydrogen. So what we get here with an asymmetric alkyne is the potential for two different products. And how are those products related to each other? Constitutional isomers, structural isomers. We'll see something similar if we take this asymmetric alkyne and we react it with our oxymercuration reagents. In fact, I could use hydroboration oxidation here as well. Since there is no more substituted, less substituted side, either of my hydration reactions would do the same thing. And it's kind of a toss-up. Do you want to do a two-step reaction in the lab, or do you want to work with mercury? At least mercury is just a one-step reaction, but on the other hand, it's mercury. So where's the carbonyl going to form? Both positions. In terms of synthesis, taking a starting material and transforming it into a product that you're hoping to acquire, this becomes an issue, having structural isomers. It means that your yield is going to be a lot lower in the lab. You're going to have to do a lot more work to separate those structural isomers from the same product. Okay, there is, I'm kicking myself all over the place today with this table. There's a few more reactions that I'd really love to see on that one, so I'm going to have to redraw some of these on the right-hand side. I think the last one I'll demonstrate up here is our ozonolysis reaction. If you use O3 with H2O2, or if you use hot potassium permanganate, so you guys remember this from our alkene oxidative cleavage reactions. If I take this alkyne, I will cleave it into two carboxylic acids. Having the carbon change that match the starting material. This is a good opportunity for me to remind you guys to practice counting your carbons throughout the semester. It can be incredibly easy to add carbons accidentally or forget carbons accidentally. So you want to count your carbons on your starting material and count your carbons on the product. I call that mapping your carbons. Make sure that you're not losing track of any of them. All right, I'm going to take this internal alkyne and we're going to show 3 more reactions with it. The first is we'll take this alkyne and we'll react it with hydrogen gas over a palladium catalyst with carbon. It's not balanced per se, because we're actually going to add H2 in excess. It is assumed that H2 is in excess. If you were to run this in a lab setting, you would have a tank of hydrogen that you'd connect to your reaction. Or for those of you that did it in our OCHEM 1 lab here, we generated the hydrogen in situ, in excess. That catalyst first adds an equivalence of H2 across the alkyne to create a cis-alkene. And then that cis-alkene reacts with another equivalence of H2, just like we saw yesterday, to go through hydrogenation. So the final product that we get here with these reagents, 2-methylpentane, alkyne to alkane. What if you want to limit the hydrogenation? What if you want to add only one equivalence of hydrogen and not 2 equivalences? Well, what you would need is for the reaction to be reactive to the alkyne, but unreactive to the alkene intermediate. So a scientist named Lindler developed a poison catalyst. It allows the alkyne to react, but as soon as an alkene forms, this catalyst inhibits the reactivity of the alkene. So the reagents that we set up here, hydrogen, and then we use something like a barium carbonate quinoline solution, which is fine and all, but a lot of places will just list this as Lindler's catalyst. So we don't need to understand what the barium carbonate is doing. We don't need to try and predict why quinoline is making a big impact. We can just remember that Lindler was the one that inhibited the reactivity of the alkene. What is the stereochemistry of that product? The Z, yeah. This is a Z alkene, it's a cis alkene. Selectively, that's what hydrogenation with Lindler's catalyst does. What if I don't want the Z alkene? Is there a way that I can partially hydrogenate, not all the way to an alkane, but leave it at an alkene and get the trans alkene? What we use here is a metal in ammonia. So I want to be very clear that this is not NaNH2. NaNH2, sodium amide, is a very strong base and a fairly good nucleophile as well. Sodium amide cannot do anything to this alkyne. It just has no reactivity. Sodium in ammonia is incredibly different. What charge does sodium have here? Neutral. This is elemental sodium. And what charge does sodium have here? A 1+. It's our cation here. We're used to seeing sodium in that 1+ state. But we're taking advantage of elemental sodium because of its reductive powers. It can take its 1 valence electron and give it away to just about anything. Now, I'm not going to ask you guys to know the mechanism for this reaction, but it is the mechanism that explains why the product is trans rather than being cis. The product has the mechanism has an intermediate where a lone pair of electrons and a radical electron sit across the 2 carbons at the same time, and non-bonding electrons repel much more strongly than bonding to non-bonding electrons repel. So they can minimize their repulsive strain by being trans to one another. Any reactions that we didn't see here that you guys remember from your OCHEM 1 experience? Oh, I do. I have one. But it's going to be a good segue for us into our substitution and elimination reaction.
How to make A-ring rings with keys.
So you might be thinking of the Diels-Alder reaction.
The one that's
The one we did
like
in
two halves. Yeah, but
the one we did in lab. Similar to the one we did in lab.
I think so. Yeah.
This wouldn't necessarily form an arene. It wouldn't form an aromatic ring. That idea that I was telling you guys about mapping your carbons, we can say that in this Diels-Alder reaction, we're going to form a 6-membered ring. And if I have a diene and an alkyne, one of the diene bonds is consumed, and one of the alkyne pi bonds is consumed. So it gives me a 1,4-cyclohexadiene product, but not an arene product. And you might be able to make it an arene product by doing allylic substitution. Take some bromine and add that bromine right here. In the intermediate, it might actually rearrange so that your bromine adds here and the alkyne or the alkene has moved, and then you could do an elimination reaction to form the benzene, but it's just a cyclohexane template, really. That's what you are thinking of? Actually, that's a good reminder. I don't do a lot of the Diels-Alder reactions in Ochem 2. You can. They involve the same chemistry. They're just not as frequently seen with the other chemistry that that we're going to be doing. So this is a good example of a Diels-Alder cycloaddition, and that's probably where I'll leave it. What I do want to show you is transitioning into substitution and elimination.
You said it was another reaction,
Yes,
but it's not
it's not an addition reaction. So I want to show you guys the alkylation of alkynes. That word is not too big and scary, right? Alkylation. What's it mean? To alkylate. But what does alkylate mean?
another alkyl group or something
Add an alkyl group. Can you name an alkyl group for me?
Is that adding like a carbon chain?
Yeah. So adding an alkyl group, adding a carbon chain. So it could be as simple as adding a methyl group, a 1-carbon chain. It could be a propyl group or an isobutyl group. There's a lot of different options here. So the process of alkylating an alkyne actually starts by having a terminal alkyne and turning it into a nucleophile. So the first thing that we need to do is introduce a strong base like sodium amide or sodium hydride, both of which are strong enough to rip away the hydrogen from that terminal carbon and leave that carbon with a lone pair. Now, how much does carbon like having a lone pair? Not at all. So it wants to share it really well. And we do have to be careful what we allow that carbon to share it with. If we allow that carbon to interact with too highly substituted a carbon, it might just run elimination. It might act as a base. So instead, we want to keep it small. We can add something here like methyl iodide. And we have alkylated the alkyne. The alkyne now has more carbons, more alkyl groups. And it's not very common that we want to separate it all out like this. Alkylation is kind of one step on its own. So let me give you another example. This time I'm going to take acetylene. And first, I'll deprotonate acetylene. Then I'll introduce ethyl bromide, 2-carbon chain with a bromine leaving group. That's going to alkylate one of my positions, leave the other one open. Then I'll deprotonate again, and I'll add one more. This is benzyl chloride. So the chlorine is attached to the carbon off of the benzene ring, off of the phenyl ring. Now this is where counting your carbons can be very useful, so I want to show you guys how to do that. I like to count through a nucleophilic attack. And it is the alkyne carbons that will attack the electrophilic alkyl halides. So I'm going to have a product with an alkyne, and on one side, I'm going to have carbon 1 attack 2, and 2 connected to 3. Then I did a second nucleophilic attack. So I'm going to map this as well, and I'll use primes to differentiate these. So 1' attacks 2', which is connected to the aromatic ring. I'll call it 3'. And so I've got 1' attacks 2' connected to the aromatic ring. So I've taken this 2-carbon reagent, acetylene, or ethine, if you use IUPAC nomenclature. And I have alkylated both sides of it. And now I have a much longer carbon chain, and I still have the potential to do chemistry at that alkyne. Any of these reactions are fair game. You got questions, Susan?
Bro, it doesn't matter that stereochemistry or anything here, right?
There's no stereochemistry at the alkyne center, luckily, and no chiral carbons either. 2 hydrogens, 2 hydrogens.
But could there be stereochemistry with alkynes?
Well, alkynes are linear,
Right.
so they have no E or Z, they have no R or S. The only thing that you would describe, and it's regiochemistry rather than stereochemistry, you could describe an alkyne as being terminal or internal. Yep. I've been using this word a bit, and I want to make sure that we understand it, that we have a good definition for it, because this is where it becomes most relevant. Nucleophile, I like to abbreviate it as nuke with a minus, even though some nucleophiles are neutral. What the nucleophile tells you is that it has an excess of electrons. And it wants to donate those electrons to a nucleus. It wants to bond to a new nucleus. And the counterpart to the nucleophile is the electrophile, which I will often abbreviate as this capital E+. Not all nucleophiles are positively charged. You can see that methyl iodide is a neutral reagent, but having that positive charge in there reminds us that the electrophile is an electron acceptor. All semester, the chemistry that we study is going to be defined by nucleophile and electrophile. And a lot of times it also is described by acid and base. And all Bronsted-Lowry acids and bases are Lewis acids and bases, meaning they are nucleophiles and electrophiles. But not all nucleophiles and electrophiles are Bronsted-Lowry acids and bases. I'm going to have to start making space over here, so if you guys need a picture of this, feel free to grab it. Now you guys have seen substitution and elimination before, so before I get too much into it, what is the hardest part about these reactions? What do you feel like is the question you still have about substitution and elimination? You don't have any questions, which is great. That means that it makes a lot of sense to you already. And all we have to do are look at some common conditions. So I'm going to give you guys this table. And this table helps us predict what type of substitution, what type of elimination, or whether it's a combination of both, a reaction is going to go through. On the first column on the left, we're going to look at methyl carbons, primary, secondary, and tertiary carbons. Now I should say that this is a table for alkyl halides. We'll have to look at substitution and elimination of alcohols after. They don't really follow this table quite as well. By putting these descriptors, what am I really analyzing? I'm going to look at a molecule and I'm going to find out which of these best describes my carbon. That means I'm analyzing that carbon's. I'm analyzing its regiochemistry. How substituted is the carbon? What else is going on around it? A more substituted alkyl halide has a lot more carbons surrounding it, which means if there's an elimination, there might be several places that elimination could actually occur from. Along the top, we're going to look at reagents that are strong bases and strong nucleophiles. We're going to look at reagents that are strong bases but weak nucleophiles. We'll look at reagents that are weak bases but strong nucleophile. And lastly, reagents that are both weak bases and weak nucleophiles. And I'll give you guys some common examples that we'll see throughout the semester for this.
There's a table on the course somewhere.
No,
Website? No.
I don't have it anywhere on my site.
But this also will change with like heat and stuff like that, right?
Yeah, we'll talk about temperature control in there. I've actually seen this table in other places, so you can find this online.
You might have something like this.
And not every table is the same. Some professors are a little bit more literal, and they'll tell you that any carbon can go through any reaction, so you can't simplify it this much. Other professors will tell you this is a good approximation for looking at making predictions. So on a methyl carbon, that would be something like methyl iodide. You cannot run elimination reactions because elimination requires 2 carbons. And it's incredibly challenging to form a carbocation because it is the least stable carbocation. So all of these reactions, regardless what type of reagent you have, at a methyl carbon, it runs SN2. And SN2 just means the nucleophile bonds to the carbon at the same time that the leaving group leaves the carbon. So we'll look at a reaction that demonstrates our SN2 mechanism. If I look at something like ethyl bromide for my primary carbon, things that are strong nucleophiles prefer to do SN2 because carbocations are not stable, but steric strain is not very high, so it's easy for the nucleophile to access. Things that are weak bases and weak nucleophiles, they also have a preference for SN2. But this reagent that favors being a strong base, at this primary carbon, it starts to compete between running an E2 reaction and an SN2 reaction. At a secondary position, we see this competition start to rise up on our strong nucleophile, strong base. These will start to compete between E2 and SN2. Meanwhile, my poor nucleophile leaves substitution. And because it's a strong base, it only starts doing elimination. On the other hand, something that is not good at being a base, but only good at being a nucleophile, runs SN2. And then we get to this point where a weak base, weak nucleophile doesn't prefer doing any reaction. So from here on out, it's just going to split its time between E1 and SN1, unless we use some temperature control. My strong bases, at my most substituted position, and I'm sorry, I just realized I haven't been doing a good job of giving you guys more examples.
You remind me why would you do E1 on the case instead of E2?
Here,
Yeah.
these reagents, weak bases and weak nucleophiles, are bad at doing their job. They're not good at donating their lone pair to form a bond to carbon. They're not good at donating their lone pair to accept a hydrogen. So the only way that they will react is if first a carbocation forms. Then they will donate their lone pair. Then they will take a hydrogen as a base. So I've given you guys examples of just abbreviated structures, and down here at the bottom I have OTS. Some of you might have seen this, some of you might not have. It is a sulfonyl group, and you can think of it as a halogen. It behaves much like the halogens do. It's actually an abbreviation, and it's a very useful abbreviation in my opinion. It's an abbreviation for this structure, O, and this is TS. So it's nice to be able to just not draw that every time. All right, the last couple of things to fill in here. At this most substituted position, nucleophiles have a very challenging time getting to the carbon. And so things that are good at being bases, they just act as bases here. But something that only wants to be a nucleophile is not a very good base, doesn't line up here well. So you would probably see a table fill this in as E1 or SN1, but quite honestly, we're not going to see it. So I'm just going to put not common to see. You just don't subject the reagent to those conditions because it's not their preferred condition. All right, I want to give you some examples now. Things that are really good at being nucleophiles, but very good at being bases. We start off with hydroxide and alkoxides. That's something like hydroxide, methoxide, ethoxide, the conjugate base of our water and our alcohols. And then we have carbanions as well. So the alkyne ion and any other carbon anion. Very strong base, but also a very strong nucleophile. There's really only one reagent that we will use this semester. Yeah, I guess there's two reagents here that are considered strong bases, but weak nucleophiles. One of them is tert butoxide. The reason that tert butoxide is not good at being a nucleophile is because of how much space it takes up. It's so sterically strained. It's very good at being a base, just like other alkoxides, but it's not good at being a nucleophile because it brings a ton of steric strain with itself. The other one is called LDA, and it is lithium diisopropyl amide, N-, not to be confused with amide, the functional group. And you can see that LDA is also very big and bulky and sterically strained. Things that are not good at being bases, but good at being nucleophiles. Some of the most common ones we'll see are the sulfides, cyanide, and azide. And by common, I mean not super common. They'll be there. But we're going to be doing so much other chemistry that when these pop up, it'll be like seeing an old friend. All right. The last thing are weak bases and weak nucleophiles. These are actually just polar protic solvents. We've got water and alcohol. You can see that these are the conjugate acids of hydroxide and alkoxide in our first column. So they are not as good at being bases. They're not as good at being nucleophiles. And then we've got this issue of temperature control. What happens in these instances where my reactions are competing? I don't want to put in 5 grams of a reagent and get out 50% an elimination product and 50% a substitution product. So in these conditions, adding heat promotes elimination, and low temp promotes substitution. There's a lot of detail packed into this one little table, isn't there? And there is one more detail that I need to share. All of these elimination reactions that can be run, the elimination reactions prefer the most stable alkene. They prefer the Zaitsev alkene, all with the exception of the strong base, weak nucleophile category. Because these are such bad nucleophiles, due to their steric strength, it starts to affect how they act as bases as well. They would prefer to go to the least substituted beta carbon, which gives us a less substituted alkene product and an anti-base of alkene. So let's look at a couple of reactions. Can you tell me the regiochemistry of the alkyl halide leaving group? Primary. Good. So now I've got myself in a row. Can you tell me the strength of my reagent, hydroxide? Strong base, strong nucleophile. Which is important because if it was a strong base, weak nucleophile, I might be competing between getting two different products. So I can predict that this is going to run through SN2. I'll substitute the chlorine for the alcohol, and I get this byproduct of NaCl. And now let's look at its mechanism. I'm going to abbreviate here. I'm also not going to show the sodium. Sodium's a counter ion. It's a spectator ion. It's not doing any chemistry in the reaction. It's just balancing charge. Hydroxide shares its lone pair with the carbon. Oxygen bonds to carbon. Chlorine breaks its bond. Because chlorine is more electronegative, chlorine takes the electrons. I don't want to draw too much attention to this, but you do have a written homework assignment that has you do some of these early addition reactions. And I get a lot of people that will show me NaOH like this. And they'll start their mechanism by taking this NaOH bond and breaking it to oxygen. What's wrong with that? Nothing's wrong with it?
They're not covalently bonded.
Right. That line represents a covalent bond. Whether that you want to look at that with valence bond theory and say that's an S to sp3 orbital, or if you want to look at it with MO theory and say that it's a sigma orbital, by drawing a line, you are saying it's a sigma bond. And it is not a sigma bond. It's an ionic bond. So I'm happy to let you guys draw in sodium as a counter ion, but there is no electrons going on. The other thing that I get is someone might draw the sodium ion. And when they show chlorine leaving, they show its electrons going to the sodium. What's wrong with that? The charge, well, the charge.
It's not negative until it takes the electrons.
So maybe they'll do something like this. Hydroxide attacks, but the bond to chlorine, they have it pointing towards the sodium. I know what they're thinking. They see that the byproduct is sodium chloride. But what they're saying is that chlorine takes these electrons and covalently bonds to sodium, which it doesn't. Chlorine takes the electrons for itself, which is what allows it to ionically bond to sodium. You can't use electron arrows to show ionic interactions because electron arrows show covalent electrons being shared or taken, and ionic bonds don't have any electrons shared. So you can't use arrows to show an interaction between ions. Is that good? All right. How easy is that SN2 mechanism? Yeah, it's like doesn't get any easier, right? It's just, I mean, you ignore all the issues I just brought up. It's just two arrows, nucleophile bonds, leaving group leaves. Let's look at an example for E2, and what I want to do here is actually look at a couple of different examples. We'll take the same molecule, and we'll react it with hydroxide, and then we'll react it with tert butoxide. Now, hydroxide is a strong base, strong nucleophile, and my leaving group is on a tertiary carbon. So I don't need to say that heat is added here. I can. It just doesn't hurt anything. It's only going to run E2. And it's going to run Zaitsev E2. It's going to give me the most substituted alkene. So here's my leaving group. That carbon needs to be in the alkene. And then here are my beta carbons. These are my possibilities for what could be in the alkene. And these two options on the left are less substituted. This carbon on the right is more substituted. That would give me my Zaitsev alkene product. Is this E or Z? No. One carbon has two methyl groups, which means that this is not a stereocenter alkene. Tert butoxide, on the other hand, being an anti-Zaitsev base, it's going to eliminate from either of those other two methyl groups. Does it matter which of those methyl groups it eliminates from? No, because they're identical. So they give the same product, maybe just drawn a little bit differently. How challenging is the mechanism for this one? Maybe slightly more challenging. It's one additional arrow, and you gotta make sure you grab the right hydrogen. Hydroxide steals the hydrogen beta to the leaving group. The electrons from that bond go to form the alkene, and by forming the alkene, the leaving group is forced out of the structure. What do you guys think so far? Good review. Too slow? Let's pick up the pace.
On that first one, you just put in the, I mean, you showed it in the third butyl, the other part, but in that first one, but also that's the major part only you're showing, because like there's more beta hydrogens, right, than just the one that you added on,
There are beta hydrogens here.
but which will form the other product over there.
Yeah, that would be the minor product.
Okay.
So with my small base, Zaitsev alkene is the major product. But with my bulky base, anti-Zaitsev alkene is the major product. And really, we did talk about some reactions give multiple products, whether that's structural isomers or stereoisomers. And sometimes you do have to work to remove those impurities.
You want to see those when we do like reactions and stuff like that, other products, or usually just for the major?
Yeah, usually just the major product. Or I'll try to make it clear if I want to see all products. Let's look at an SN1 mechanism. So I want to take this tert butyl group connected to OTS, and we're going to react this with methanol. Will the functional group in my product be an alcohol, an ether, or an ester? reacting with this tertiary carbon with methanol, will the functional group in my product be alcohol, ether, or ester? Good. Alcohol as a reagent is a precursor to an ether. If you want to make an alcohol, you actually want to use water as your reagent. Water is the precursor to alcohols. Alcohol is the precursor to ethers. So this is the product that I get at the end. And I have a byproduct of HOTS, but it's not the most important part of this reaction. I'd rather focus on the...
Wait, that's an ether?
That's an ether. It's an oxygen with carbon on ether side. What do you think it is?
I just messed it up in my head.
Now in this mechanism, I'm going to show everything that's present throughout the reaction, but not everything is involved in each step. SN1 and E1 mechanisms share the same step. First, the leaving group leaves. First, a carbocation forms. And now that the leaving group has left, now that a carbocation exists, my weak nucleophile is able to do whatever it wants. Oh, and look, our table tells us we should be expecting a mixture of products, both an elimination product from this reaction and a substitution product. So what could I change to the reaction arrow up above if I wanted to only isolate the substitution product?
Temperature.
Yeah, just say something like low T. Run this cold, and you can promote that substitution product. All right, back to the mechanism. Now that a carbocation has formed, my weak nucleophile is willing to share its electrons. When it does this, it takes on a positive charge. Now it's got 2 bonds to carbons and 1 bond to hydrogen. Is it reasonable to think that one of those bonds to carbon might break and the other wouldn't? Or is it more reasonable to say the bond to hydrogen is most likely to break? So this is acidic conditions. That ether right now is protonated as an acid. So it makes sense to simply deprotonate it. And like I said, that gives us a byproduct of tosylic acid, TSOH. Yesterday, I showed you guys different ways that you can show your mechanisms. SN2 and E2, they can only be shown one way because they are one-step reactions. But SN1, I'm showing this fully sequentially. You could also show it step by step. And I want you guys to practice doing whatever clicks the most in your mind. I'm happy to accept any type of mechanism. I had a student in the spring who he saw mechanisms in 2 parts. So he would do a series of steps, and then he would start over and do another series of steps, rather than doing everything as one big series or doing each thing step by step. And that worked for him. So find what works for you. All right, let's do an E1. And this time, we're actually going to look at how it takes on the ability to do a rearrangement with our carbocation. I guess actually this isn't a great one to show that it rearranges, but that's okay. That triangle, delta at the bottom, what does it represent? That's our heat, telling us that we're promoting elimination. And here's my major product. What's the first step of my mechanism for E1? That's right. The leaving group leaves. Carbocation forms. Same as SN1. Now that I've formed this carbocation, I need to consider whether it's in the most stable spot. And in this case, it's not. It's adjacent to a more stable spot. So there's a good likelihood that this carbocation rearranges before the elimination actually takes place. Okay, now I want to have a discussion with you guys about plausibility. Few reactions are ever run in a lab at large quantities, especially in a teaching lab like what we have here. Instead, you might run a reaction with maybe 0.1 moles or 0.01 moles of a reagent, which means that you're taking, instead of 600 million billion molecules, 1 mole, you're taking about 0.6 million billion molecules. So still like an absurd amount of molecules. There's a lot of water surrounding those 0.6 million billion molecules. A lot of molecules of water. So there is a really good chance that water acts as the base here. There is some bromide ion floating around, so there's also a chance that bromide acts as the base. Both of those are plausible. Which of them is a better base, bromide ion or water? Water is a better base. When bromide acts as a base, it forms HBr, which is a strong acid, meaning it doesn't really exist in solution. So it's plausible that bromide could take the hydrogen and act as the base, but it's much more likely that water will take the hydrogen and act as the base. The reason I bring this up is your mechanisms throughout this semester may look a little bit different from mine. But as long as they are plausible, then I'm okay with that. If you had said that water takes the hydrogen as the bromide leaves, incorrect. That's not the mechanism that E1 follows. Or if you had said, at the same time that bromine leaves, the hydrogen shifts. I don't think that's very plausible. Maybe it does happen because you've got billions and billions of opportunities for it to happen. But it's much more plausible that it happens sequentially. So as you do your homework with your written mechanisms and as you do your unit tests, preparing for the exams, those are the types of things I'm going to give you feedback on. You've combined these steps. You're saying that all of these things have to happen at the same time. And it's much more plausible that they happen sequentially rather than at the same time.
Do you mind if we don't put like the H2O or the H2O and Br on the steps where they're not being used, like just leaving them out?
So I give a list of things that I like to see, and one of them is byproducts at each step.
Okay.
So when the bromine kicks off, I do want to see the
You
Br
wanna see it,
minus.
but it would be okay if it didn't have the H2O.
That's correct. You wouldn't need the H2O until here.
Okay.
And after this step, you wouldn't need to show the Br minus.
Okay,
Because
just
it's
see
no
the
longer-
byproducts of that step.
So I like to see the byproducts at each step. I like to see that you know where the things are going after they've left your molecule. But if they're not relevant after that, then that's okay. What I will do this semester though, and feel free to copy the notes as you will, what I'm going to do is take each reagent that will be involved in the mechanism and show it at each step, and then tie it in only when it's involved. Textbooks don't always do a great job with mechanisms. So I've linked this free textbook online, and if you look at some of the mechanisms, they will say things like proton transfer happens between this step and this step. And they don't show the proton transfer, they just say proton transfer. And it can be confusing because it's like an OH group over here that has an extra proton, and then in the next drawing, it's an NH group in this part of the molecule that has a proton. And all they say is proton transfer. Plausibly, a base takes this hydrogen, and then later an acid gives this hydrogen. Less likely, very implausible, is it that those two groups would ever exchange the hydrogens themselves directly. So there's going to be mechanisms that I will come around and give you some feedback on. I don't want you to show those steps together because that's just not plausibly how it occurs. Okay, how are you guys feeling on all this fun stuff? Great. Just a few extra reactions. Anybody need a picture before I erase it? Just a few extra reactions to cover, and those are our reactions with alcohols. So alcohols can be substituted, eliminated, and even transformed. But the reagents don't resemble what we do for alkyl halides. So first I want to look at inorganic substitution for our alcohols. When we take a reaction, when we take an alcohol and we react it with thionyl chloride, SOCl2, the alcohol acts as a nucleophile. It bonds to the sulfur, which kicks off a chlorine, which then can break the bond between carbon and oxygen because oxygen is now bonded to sulfur as well. And so we can use SOCl2, thionyl chloride, to give us an alkyl halide, a chloride. It's kind of interesting to see the byproducts here. We make sulfur dioxide and hydrochloric acid. So you can see where the second equivalence of Cl goes. It actually takes the alcohol's hydrogen. And we have a similar reagent that we can use to make an alkyl bromide, PBr3. And the byproduct is not as fun, it's just PBr2OH. So it's pretty much exactly what you'd think. Now you can make these same alkyl halides using acidic conditions. But the difference here is the potential for carbocation rearrangements. If I take an alcohol and I react it with HCl, then I will protonate the alcohol, which kicks off a molecule of water. And this does so in an SN1 mechanism, we can see that it's SN1 because of the rearrangement. And we can do the same thing with HBr. I want to say, I don't think that my reagent does a great job comparing the effect of inorganic and acidic. So I'm going to make a slight change. I'm going to add this methyl group to my starting material up here, which means that it adds to my products as well. What this highlights now is that inorganic substitution avoids carbocation intermediates, avoids rearrangements. Acidic conditions cannot avoid carbocation intermediates. Okay, and now the last one is the transformation into those thionyl groups. Excuse me, I said thionyl, but I meant sulfonyl. So if I take an alcohol and I react it with tosylic chloride, TSCl, the hydrogen gets removed from my oxygen. Essentially, the hydrogen is substituted by the TS group, the tosylate group. Now this could be really useful if I want to run an elimination on the alcohol. And I want to do maybe an anti-Zaitsev elimination here at the less substituted carbon. I could add in my big bulky base. But for reasons that we're going to see right now, elimination of alcohols is difficult to control. In order to eliminate alkyl halides, we introduce bases. In order to eliminate alcohols, a base won't be effective because a base will simply deprotonate the alcohol. It won't eliminate any other carbon. So instead, we need an acid. The acid protonates the alcohol, makes it a good leaving group, and then allows us to run an elimination. So elimination of alcohols, always Zaitsev. And if you don't want Zaitsev, then you should probably change your alcohol to something else that you can then use an anti-Zaitsev base with. All right. Guys, I know I've really just been like slamming you with reactions left and right. I apologize for that. I know it can feel dry. It's a little boring. I'm gearing you up for what the semester is going to feel like. No, it stays the same. It stays just as boring. Oh, well, that will stay the same too. It will stay a lot. I think that one reaction we haven't really seen is the elimination from alkyl halides into alkynes. And those are pretty straightforward. We can use the same reagents. What I actually want to spend a little bit of time on right now is looking at like a synthesis. So I want to take this methyl cyclohexane and I want to convert it into cyclohexanone. When doing a synthesis, or a retrosynthesis. I always encourage you to start by mapping your carbons. Figure out what carbons are being added, what carbons are being removed, where is the chemistry happening. Then I encourage you to brainstorm. What functional group do you have in the starting material? What are all of the things you can do with that functional group? What functional group do you have in the product? What are all of the ways you can form that functional group? And then the last thing that I encourage you to do, and this kind of goes in with brainstorm, is work forward and backwards. Don't just try to take the starting material and brute force your way through the synthesis, because there can be a lot of different things you can do at any given step. But take that final product as well and figure out what it came from, and then you can meet in the middle and figure out where you're at. Now, the first reaction that we're going to use in this is actually one I think I missed when we spent an hour and more, 2 hours, reviewing reactions. So,
What is the last stage?
work forward and backwards. So try to figure out where you can go from the starting material, but also figure out where you could come from to get to the product. And then sometimes you meet in the middle with a better understanding of how to get there. Now, when you have an alkane structure, you can't do an addition reaction, you can't do an elimination reaction. So the only thing that can be done on an alkane is substitution. And it has to be radical substitution. So we'll use NBS or Br2, and we'll expose it to light, and we'll get the most substituted alkyl halide. Well, where can I go with that alkyl halide? I can, do you know what I did? I skipped the very first step, and I'm not doing a good job of demonstrating to you guys how to use my tips. First, we should have mapped the carbons. Do you notice anything that's happening with the carbons in the course of this synthesis?
I was saying,
I disagree.
Well, from the beginning to the first reaction.
Yeah, but I meant the full synthesis.
So one of the methyl groups.
Yeah, methyl group goes missing. So my chemistry needs to be involved around that methyl group. That's for sure. And at some point, I will need to get rid of that carbon. So let's brainstorm. This was me kind of giving you the brainstorm. The only thing I can do with an alkane is radical halogenation. There's just no other reaction for us to do. So I can radical halogenate. And it adds at the most substituted position because that's where the most stable radical forms. What other things can I do? What other reactions involve ketones? This is part of that brainstorming. What are my possibilities?
You mean like to get the O up there?
At some point, I'll need to get an oxygen, but not just an oxygen, a specific functional group, the ketone.
Isn't it if you make that an alkene and then you do O's analysis and that splits off?
There you go. So, to break it down, first, recognize the functional group, ketone. Second, recognize the reactions that can form a ketone. Ozonolysis can form ketones. So far, that's it. Oh, no, that's not true. Oxymercuration of alkynes. The acid hydration of an alkyne can also form a ketone. I don't think that I can form this from an alkyne. I'd have to have a triple bond within the ring. And how am I getting rid of that other carbon? So this is where that brainstorming is effective. What can I do and what doesn't make as much sense to do? And then you've got this idea, which is, if I can form this from ozonolysis, it means that I need an alkene precursor. And I need an alkene where this carbon is a part of the alkene. And this helps explain where my lost carbon goes. I'm going to do ozonolysis and cleave this carbon off completely. Now, we're not focusing on the byproduct, what happens from this. So we could use either type of ozonolysis, but I'm going to use oxidative ozonolysis. The reason is that one carbon is going to form carbonic acid, H2CO3, and carbonic acid decomposes into water and carbon dioxide. So it basically gets rid of itself in my reaction. Okay, so here what I have done is worked forward and backwards. I figured out the most reasonable starting point and the most reasonable ending point, and now I just have to connect them. What reagent will do this elimination for me?
H2SO4.
No, H2SO4 will not do anything to that alkylate.
Just elimination.
Elimination. But can I use any elimination reagent? I want to make sure that I don't get the Zaitsev alkene. I need to get this anti-Zaitsev alkene. So recognizing the regiochemistry of the product informs you about what reagent is necessary.
You have to use the terp butoxide.
Good. Use terp butoxide. Gives me the anti-Zaitsev alkene. I'm good to go. Okay? Synthesis is a challenge. It's a fun challenge in my opinion, but it is a challenge. And so throughout the semester, you're going to have written homework that has you do mechanisms, but you're also going to have written homework that has you do syntheses. Because that is my opportunity with your written homework to check in with you before you get to the unit test and have to do a synthesis on the unit test, and before you get to the midterm and have to do a synthesis on the midterm. The homework is my first opportunity to step in and say, what other reactions did you consider doing? Try doing this one again because your regiochemistry was flipped or something like that. And yet I try to keep them short. I try to keep synthesis problems to within 3 or 4 steps max. Like this is a 3-step synthesis, and you guys might agree, like that's not incredibly hard to solve, but it just takes practice, and it takes knowing your reagents, and so we'll be doing that throughout the semester to get you used to it. All right, Caesar?
Is there any other reagents that you could use for anti-Zaitsev?
Yeah, you could use LDA, lithium diisopropylamide.
One of those, you know, that I wonder how we did this to be able to do this kind of stuff before.
Is it possible that you're just not used to seeing LDA, or sorry, that you're just not used to seeing terp butoxide written this way?
We didn't use that either.
We did elimination, we didn't try to go for it.
Anti-Zaitsev?
Well, okay, I see what you're saying. Yeah, so we just didn't realize which one was the most common, which one's the least common. We just did all of them, like if it was multiple products, we do all the products. So it could be anything else that has that kind of base.
Oh, okay. Interesting.
Yeah.
Yeah, I mean, if you did this with hydroxide, you would get that product.
It's just a minor product.
Yeah, maybe like 5%.
Yeah, that's why it's confusing a little bit. Why is this a major product here? Based on what you said earlier, how is this?
Yeah, just our base. The nature of our base.
So just remember, if we need this anti-Zaitsev, this base here.
That's right. Okay, guys, so we are almost up for time. I want to lay out the game plan for our next class period. First, try to tackle these mechanisms. You've got substitution or elimination, substitution or elimination. These are first order reactions. No, you know what? I've got this wrong. This is a second order reaction. This is a first order reaction. I thought I fixed that. And then you've got an addition reaction to do as well. So try to work on those. I'm happy to allow you to resubmit as many times as you want to get full points for it. And I will be giving you feedback on it. This is the only homework I'll give you feedback on rather than on active as well. Now the other thing I want to talk about is when we come back in tomorrow, we've got a lot to do when it comes to spectroscopy. So we're gonna try to cover all of our major types of spectroscopy, but because it's not going to be a huge part of your grade in this class, we're going to kind of glide over some of the details. So mass spec, one of the least useful types of information we can get. We'll look at mass spec and we'll just look at it as quickly as we can. Mass spec gives us molecular mass and maybe the major structure, the stable structure. We're going to spend a lot of time on proton NMR because proton NMR can tell you what the structure is. It tells you how everything is connected. And we're going to spend a lot of time on IR because IR can tell you what functional groups you have. And so these two are by far the most useful. If you couple what functional groups you have and how your structure is connected, you can build the structure. So we'll look at that tomorrow, and we'll maybe get a chance to briefly review nomenclature. But we're going to do some more nomenclature in our next section as well. So I'm not too worried about how your unit test has maybe 1 or 2 questions on nomenclature, but I'm not worried about how you'll do on it because they are not challenging nomenclature problems. All right, have a good night. I'll see you guys tomorrow morning.